matter in our surroundings. What is meant by matter? First of all, matter is anything which occupies space and have mass. Suppose this if you take this water bottle, it is occupying some space and has some mass. That's why we can say this water bottle is a matter. And the pen, laptop, tablet, book, notebook, anything which occupies space and have mass is a matter. Even the sand or the food, these are all called as matter because they are occupying space and have mass. And what is this matter is made up of means this matter is made up of particles. Suppose the water in this water bottle can be called as a matter, and this water is also made up of particles, but those particles we can't see with our naked eye, but they are made up of very tiny number of particles, like millions of particles. That's why this matter, we have to study about this matter further, like how these particles will make different states of matter like solid, liquid, gas, and how this matter study will help us in understanding our surroundings much more. So next, move to the next slide. So there are some characteristics of particles of matter. The characteristics is that the particles have space between them. That means if you take this and these particles of matter, these particles, they have some space between them, gap between the particles. So we can prove that if you take a glass of water and take some salt and add this salt into this water, and first of all, before adding the salt, measure the volume of the water. Let it be some 100 ml, and after adding this salt, if we again measure the volume of this liquid water, we can observe that the volume will not change, but still 100 ml only. If we add another spoon of salt, then also we may observe 100 ml only, but after adding third spoon of salt, we may observe some little bit of change, like 1 or 2 ml, something like that. So for the first 2 spoons of salt, the volume of this glass of water is not changing. It is because we can prove it is because there is gap between the particles. So here the matter is water. Water can be called as a matter because it is occupying space and it has mass. So water is a matter, and there is gap between the particles of water. That's why after adding salt also, there is some the volume is still 100 ml only. So we can prove that there is space between the particles of matter. The first one is proved. The next one is that the particles of matter continuously moving. That means if you take suppose this is incense stick we use in puja, right? And the particles and this incense stick is a matter because it is occupying space and having mass, and the smoke it is releasing also is a matter because it is occupying some space and has some mass, and so these particles of smoke from the incense stick is continuously moving. Because how you can say it is continuously moving? Because even if we are far away from this place, we can smell this, right? So that means the particles are continuously moving. This is proved, okay? And if particles are in motion, then they will have some velocity, and then kinetic energy, you know that the formula is half into mass into v square of the velocity. If particles have velocity, then we can say that they are moving with some energy, like kinetic energy, half into m into v square, because they are having mass and they are moving with some velocity, half mv square. And if you increase the temperature, suppose in the first example, if in this glass of water, if you want to add some 10 spoons of 10 spoons of sugar just in this water, and in the same quantity of water, again let's take 100 ml, 100 ml of water, 100 ml of water, and the same 10 spoons of sugar. And if it is done by student A and it is done by student B, and he is adding 10 spoons of sugar directly into this glass of water having 100 ml, and the second student B, who is intelligent, is mixing 10 spoons of sugar into it by putting this glass on stove by using burner. So when temperature increases, these 10 spoons of sugar which we put into this beaker will mix with water, at a faster rate, because when temperature increases, what happens is the kinetic energy increases and the particles will move more rapidly, and thus the mixing happens more quickly. That is nothing but diffusion. That process is called diffusion. That means intermixing of particles on their own is nothing but diffusion. If temperature increases, what happens to diffusion? We can say that from this example, if temperature increases, diffusion rate increases. Diffusion rate increases. If temperature increases, diffusion rate increases. So okay, now next second characteristic is over. Now we will talk about number 3, attract each other. So particles of matter attract each other. So how can we say that the particles of matter attract each other? So by this example, if this is surface of water, and we will just sometimes play with on surface of water, like cutting the surface of water, right? If you cut the surface of water, immediately after cutting the surface of water, the water again comes and regains its original state. That means we can say that the particles are having some attraction towards each other. That's nothing but force of attraction. That attraction force is called force of attraction between the particles of matter. So in between the particles there is some force of attraction. We can prove this from this example, and we can also say that if you take a piece of chalk, and if you want to cut this piece of chalk into half, we have to use some force, otherwise it will not cut. So that also shows the particles of matter are attracting towards each other, and we have to use some force, otherwise force is not required. So we can say this is also proved. Thus these characteristics of particles of matter are very important. Okay, and next move to another topic, states of matter. We have 3 states of matter generally: solid, liquid, gas. Solid state, liquid state, gas state. But we also have 4th and 5th state, like plasma state, and Bose-Einstein condensate. This is 5th state of matter, this is 4th state of matter, generally called as 4th state, 5th state of matter, and we will talk about this in the last slide. Now we will restrict ourselves to 3 states of matter. Generally we everywhere we can see solid state, liquid state, and gas state, and these have some sub characteristics, like the boundary of different states of matter, rigidity or fluidity, compressibility, volume, space between particles, and another one is kinetic energy. So these are the ones. If you take the shape, solids, suppose if you take a table, this is a table. This table has a definite shape, because the shape will not change, because you can say that the table shape is something rectangular or square, something like that. So shape is present in solids. In liquids we can't say, because if you take 100 ml of milk, and if you pour it into a glass, it will take the shape of the glass. Into a beaker, it will take the shape of a beaker, this 100 ml of milk. So the shape of liquid is not definite, and for gas, so not definite into. And gas also, they will take the shape into which we will fill. If it is circular, it will take circular. If it is rectangular, rectangular. So no definite shape in gas also. For boundary, we can say that for a table, we can say that this is the boundary. So definite boundary is there. And for liquids, the no definite boundary. And gases also no definite boundary. Obviously, you can say from your intelligence. And rigidity and fluidity, if you take, fluidity means which flows is called a fluid. Liquids flow and as well as gases also flow. That's why whenever if you say fluids, just 1 second. That's why fluidity means, or you can say fluids means both liquids as well as gases. These are called fluids. These two show the characteristics of this fluidity characteristic. So liquid is a show fluidity, gas also show fluidity. But solids are rigid in nature. That's why rigidity is there in solids. This table is very rigid. We can't change the shape of the table easily. Rigidity means difficult to change the shape. Difficult to change the shape of a body. Change the shape of a body. Then it is called rigid in nature. So solids are rigid. Liquids have fluidity. Gas also have fluidity. And if you take compressibility, can you compress this table into, suppose this table is occupying this much of volume, and can you compress to this much of volume the table? You can't compress, right? So solids are incompressible, or you can say compressibility will not be shown by the solids. Liquids show some up to some extent the compressibility. We can also say, we can say that liquids are compressible up to some extent, and gases are highly compressible. Highly compressible. How you can say gases are highly compressible? The best example is in the kitchen itself. The gas cylinder, that is when the gas is highly compressible, highly compressed into a liquid state. So generally the LPG cylinders, the petroleum gas is liquefied. That's why LPG, liquefied petroleum gas, LPG. This petroleum gas is in liquefied. It changed into liquid state by compressing, so that it occupies less volume and we can use more amount of gas. In the same way, CNG, you can say CNG autos, compressed natural gas. This is pollution free. That's why CNG autos are much good for the environment. So the natural gas is compressed so that it is in the liquid form, but it is the fuel, as a fuel we will use it in the form of gas. In the same way, in our kitchen also we will the fuel is used in the form of gas, but it is stored in the form of liquid. So gases are highly compressible, liquids are low compressible, solids are incompressible. And the volume, if you say solid, we can say solid has a definite volume. So and liquids also have definite volume, because if you take 100 ml of some liquid, the same liquid will be present even if you put in any number of containers, the 100 ml is present. So volume is fixed, and in solids also. But in gases, what happens is that the gas, if you fill in a small chamber, and if the same amount of gas is filled in large chamber, it occupies the entire chamber, and the volume of the gas will increase, and here the volume is less. So we can say that the volume is not definite in gas. And space between particles is that in solids, like if we take some table, the particles in the table will be very much close to each other. We can also say that the space between the particles in solid is negligible, or you can say very less space between the particles. In liquids, we can say moderate space is present. Like if you take water particles, the particles may be like this, some gap is present, moderate gap. So moderate space is present in liquids. In gases, the space between particles is very much high. Suppose in this chamber the particles may be like this. If a large chamber is taken, the particles will be much more gap is present between the gaseous particles. So space between particles is very much high in gas. That's why kinetic energy is also high in gases only, because they can move faster, and the van der Waals forces of attraction between the gas particles is very less. When force of attraction is less, the particles can move very easily. So half into m into v square, that kinetic energy, velocity increases, kinetic energy increases, and so is more in gaseous state. The kinetic energy as well as the space between particles is high in gases. Okay, now the basic question is, just one second, can matter change its state? Here the question is, can matter change its state, like solid to liquid state, liquid to gaseous state, or solid to gaseous state directly? Can the state of a particle of matter can be changed or not? The answer is yes. The matter can change its state, but how that is possible? How a solid is converting itself into liquid and into gas? And we can observe in the environment also that a solid can change into liquid and liquid into gas. The best example is that in Himalayas, snow is present, and the snow is in some somewhat solid state. You can also say some ice glaciers. So these ice glaciers will melt, and they form water. It is in the liquid state, and this water will flow in rivers, and from the rivers, what happens is that this evaporation occurs, and through evaporation, what happens? The water will become water vapor, and this water vapor moves into the layers of atmosphere, troposphere, ionosphere. You know that these are layers of atmosphere. This water rises, and this water will become clouds, water vapor. And during rainy season, or if these particles will become more big in size, the clouds can't withstand this, and they release these particles, these liquids, in the form of this water vapor, in the form of liquid state again. That means water vapor to liquid. This is nothing but condensation. This process we call it as condensation. Through condensation only we are getting rain. That's nothing but, this liquid is nothing but rain or rainfall. So this is what's happening in our atmosphere naturally. So now we will again talk about this change in states of matter, how in the nature occurs. This evaporation, condensation, all these we will talk about. Don't worry. So now the basic question is, can matter change its state? Yes. How means? By changing temperature and pressure. If you change the temperature, the state of matter can be changed. How means? We will first learn the basic definition of a melting point, and after that boiling point. What is meant by boiling point? And after that we will talk about sublimation, and after that we will talk about LPG and CNG. Okay, first of all, if we change, okay, what is meant by melting point? Melting point means the temperature at which a solid melts to become a liquid at atmospheric pressure. At the atmospheric pressure, what is the atmospheric pressure? It is 1 atmosphere. Generally atmospheric pressure is taken as 1 atmosphere. 1 atmosphere is means 1.01 into 10 to the power of 5 pascals. This is the atmospheric pressure. At this pressure, when a solid melts to become a liquid at a particular temperature, this temperature is nothing but melting point. So melting point means solid to liquid occurs at particular pressure, atmospheric pressure, and at a particular temperature. This temperature we will call it as melting point, and this melting point can also be called as fusion point. Fusion point. Fusion is nothing but change of solid state into liquid state. This change is nothing but fusion. While solid to liquid, when the state is changing, it is called fusion. So here is the basic question. When a solid melts, its temperature remains the same. So this solid is changing to liquid, but the temperature is constant. Temperature remains the same means temperature is constant. So let me explain. Suppose this is water at 0 degrees Celsius, and this is ice at 0 degrees Celsius. So water at 0 degrees Celsius and ice at 0 degrees Celsius. When water is converting to ice at 0 degrees Celsius, the solid, this this ice at 0 this ice at 0 degrees Celsius is melting to water at 0 degrees Celsius. This is nothing but the melting point at which a liquid is changing into, at solid melting into liquid. Okay, so here there is if ice is changed to water, there will be some amount of energy. Some amount of energy is required. This amount of heat energy required to change 1 kg of a solid, you can say 1 kg of ice, into liquid. This is this water. Okay, liquid here water, and this solid is ice at 0 degrees Celsius. At atmospheric pressure is nothing but melting point. So there will be some amount of hidden heat energy. Latent means hidden. So when ice at 0 degrees Celsius is changing to water at 0 degrees Celsius, then there will, the heat energy is required, right? The heat energy, even if we heat it until the ice at 0 degrees Celsius is converted into water at 0 degrees Celsius, the heat energy will be taken to just change the state from solid to liquid. That hidden heat is nothing but latent heat of fusion. I will explain it again. Okay, let's stay here in this example. This both are same only, latent heat of fusion and latent heat of vaporization. This is fusion is related to solid state to liquid state. Then we will call it as latent heat of fusion. Fusion means melting point, solid to liquid. This is latent heat of fusion. In latent heat of vaporization, it is liquid to gas, liquid to gaseous state. That is latent heat of vaporization. So what happens is that here also 1 kg of 1 kg is taken, here also 1 kg is taken, and both are at atmospheric pressure and their particular melting point and boiling point. So suppose water boiling point is 100 degrees Celsius. Boiling point means the temperature at which a liquid starts boiling at the atmospheric pressure. Atmospheric pressure means this 1.01 into 10 to the power of 5 pascals, that normal atmosphere. So if you put some water in a beaker, and if we heat the water in our kitchen, what happens is that when water reaches 100 degrees Celsius, the liquid starts boiling, and the liquid changes into gaseous state. That means vapor state, water vapor. So 100 degrees Celsius is the boiling point of water. So what happens is that when water reaches boiling point, we are still giving the heat source. And if you put a thermometer into the water, into the water, the temperature of thermometer will not change from 100 degrees Celsius. So when water is okay, we'll take a beaker and we are giving a burning source, and this water is at this is the thermometer. Okay, let's say this is thermometer, and it is showing the reading of 100 degrees Celsius because water is slowly converting into vapor. Here vapor state. But but when it is converting into vapor state, water to liquid to gaseous state, the heat source is still we are giving, but the temperature will be at 100 degrees Celsius only till all this water change into vapor state, because there is some the heat is in the form of hidden. Why we will call it as hidden? Because the when a change is happening, solid to liquid or liquid to gas, the gap between the particles here, solid particles will be very much near to each other. So forces of attraction forces of attraction will be present in solids. Okay, in the same way in liquids also, the particles will have more gap and the forces of attraction will be somewhat less when compared to solids. So let's say here some less force of attraction, but to break these forces of attraction and to widen the gap, some energy is required. So we talked that particles of matter are forces of attraction. We can take example is a chalk piece. If you want to cut the chalk piece with a knife or even if with our hands, we have to use some force, otherwise it will not break. So it needs force, means the particles of matter have forces of attraction forces between the particles. So to break these forces of attraction, the heat energy is utilized until this solid state is converting into liquid state. In the same way, liquid state into gaseous state. Here liquid to gaseous state. Okay, so in ice and water case, the solid to liquid, the forces of attraction in ice will be the water particles will be ice particles in the form of solid. So the particles will be close. Here the particles will have some gap. To widen the gap, some force is required, some energy is required. This energy is given by the heat source, heat energy. And ice at 0 degrees Celsius need very little amount of energy. It can taken from atmosphere only. Atmospheric energy is sufficient to change from ice to water. Okay, so this heat energy is in the form of hidden form. This hidden, in Latin it is called as latent. That's why we will call it as hidden heat of vaporization or latent heat of vaporization, hidden heat of fusion or latent heat of fusion. Okay, in the case of melting point, solid to liquid, and it is the hidden heat is called latent heat of fusion. In the case of liquid to gas, it is called vaporization, and the heat is nothing but latent heat of vaporization. And here is also for standard purpose, that means across the world we have to use the same definition. That's why we have to take 1 kg, here also 1 kg. And at what point? At atmospheric pressure. This is also at atmospheric pressure only. At its melting point, this is at its boiling point. Okay, this is about melting point and boiling point and latent heat of fusion, latent heat of vaporization. Okay, now we can move to the next slide. Sublimation. First of all, sublimation means solid to liquid to gas. This is what we have seen in earlier, like solid to liquid, melting point or fusion point, liquid to gas, boiling point. Okay, or we can also say that boiling point is nothing but vaporization point or boiling point, melting point or fusion point, solid to liquid, liquid to gas. But sublimation means this liquid state will not be present. Directly solid to gas or gas to solid is nothing but sublimation. That means solid to gas or gas to solid, vice versa, solid to gas or gas to solid, that is nothing but sublimation. Examples is ammonium chloride. If you take ammonium chloride, NH4Cl, if you take this NH4Cl in a China dish, okay, take this in a China dish is nothing but just a beaker which is very much accurate in taking the amount. Okay, China dish is it is very much accurate. That's why we will take China dish. And if you take some funnel like shape, some funnel and covering this NH4Cl powder, NH4Cl, sodium ammonium chloride. And if you heat this one ammonium chloride, what happens is that this NH4Cl, which is in solid state, will directly convert it into water vapor. We have to close this with some cotton plug or some rubber plug. We have to close this one, and NH4Cl will directly converts into vapor state. But what we learn is that solid first state to liquid and after that gaseous state. But here NH4Cl, solid to gas directly changes. So this process is nothing but sublimation. And in the same thing happens in dry ice. Dry ice means solid carbon dioxide. Solid carbon dioxide is called dry ice. What happens in solid carbon dioxide is that carbon dioxide is a gas, right? When this gas is compressed, this carbon dioxide gas, it will directly convert into solid state, solid CO2, without any liquid state. That's why in liquid state is not present. That's why this solid CO2 is in the form of dry state. So dry ice, that's why it is called a dry ice. So carbon dioxide to solid CO2, nothing but dry ice, is also an example of sublimation. And in the case of our in homes, we will see camphor. This is the camphor. So this camphor, if you burn, this solid state will directly convert into gaseous state, vapor state. So solid to vapor state in case of camphor. So this is because there is no liquid state here. That's why it is an example of sublimation. Naphthalene balls. This you will see in toilets also, in houses we will see in the clothes, right? Clothes. This will also decrease day by day, and it will disappear because it is directly changing from solid to gaseous state, solid to vapor state or gaseous state without any liquid state. So example of sublimation. So ammonium chloride, NH4Cl, dry ice, camphor, naphthalene balls are examples of sublimation. Okay. Now, so we have proved that states of matter. Now we proved that states of matter, solid, liquid, gas, change from one state to another state. So another case is proved. Now we will talk about evaporation. Okay. First of all, what is meant by evaporation? What is the difference between evaporation and vaporization? Vaporization is nothing but when boiling point occurs. At boiling point, vaporization occurs. For water, the boiling point is 100 degrees Celsius, and at 100 degrees Celsius it changes the state from liquid to gas, liquid to water vapor. If in the case of water, it is nothing but vaporization, or you can say boiling point. But evaporation means E, like, just remember, E means before vaporization, evaporation occurs. Before vaporization means like before boiling point. Vaporization point is nothing but boiling point. Before boiling point, if before boiling point, if liquid converts into gaseous state, it is nothing but evaporation. So generally in rainy season, in our India, we know that our roads are like this with so many pits. Okay, in every state we will see these kind of roads, and in the rainy season these are filled with water. After some 2 days or 3 days, if rain is not present, if rain doesn't occur, what happens to this water is it will disappear, or some only little bit amount of water will be present in this pits, because the water here will change into vapor. But we are not boiling this liquid at 100 degrees Celsius. We are not boiling this water present in the ground at 100 degrees Celsius, but the water is still disappearing. Okay, you can say that the ground will absorb some water. Yes, groundwater will increase because groundwater increases in terms in case in a rainy season. Because of this water, soil absorbs some water, okay, but some amount of water will also goes into the environment again, because in the form of water vapor, especially in summer season. If the same amount of water is present, rate of evaporation rate of evaporation rate of evaporation let it be called ROE, rate of evaporation. This rate of evaporation is more in summer when compared to the rainy season, because the temperature is less. So temperature influences this rate of evaporation, right? This is a natural phenomena. So some amount of water will evaporate before boiling point. We are not boiling at 100 degrees Celsius, but the water is converting to vapor state. This is nothing but evaporation. So liquid to vapor takes place without the liquid reaching the boiling point. The liquid is not reaching the boiling point, but the liquid is changing to vapor. That's nothing but evaporation. Definition is the phenomenon of change of a liquid into vapor at any temperature below its boiling point. For water it is 100 degrees Celsius. Below its boiling point is called E for evaporation. So let's see what are the factors affecting this evaporation. So rate of evaporation is how is influenced because of temperature, because of surface area, because of wind speed, because of humidity. How rate of evaporation will change. So if you take temperature, if temperature increases, like we talked about rainy season and summer season, temperature here is less when compared to summer season. So when temperature increases, what we discussed here is rate of evaporation will increase. But why rate of evaporation is increases? Because when temperature increased, this water have the particles, this is a matter and it will have some particles of matter. These particles, the gap is like this, okay. It is converting into vapor state, water vapor. In this water vapor, the particles gap will be like this. So more gap is present in this, okay. So here the force of attraction is more, here the force of attraction between particles is less. So it is changing. To change from this state to this state, the energy has to be less. The energy has to be, here the energy is required so that it can change from this position, first position to second position. That means water to water vapor. So that energy is taken from the surroundings. So the surrounding temperature, in case of rainy season, let's say some 25 degrees Celsius. In summer, let's say 35 degrees Celsius. You know that in summer, in some cities it will be 40 also. So 40 degrees Celsius temperature also. So let's take 25 degrees Celsius and 35 degrees Celsius. So when the surroundings are at 25 degrees Celsius, it can take only little bit amount of heat energy, and so the rate of evaporation will be very slow in process, very gradually it will change. But in case of summer season, the temperature is very high, so it can the heat energy will be very much is easily achieved by these particles, and so they can easily move from this state of matter to this state of matter by breaking these forces of attraction. So that's why when temperature increases, rate of evaporation increases. We proved the first one. Now the next one is SA. SA means surface area. What happens if surface area increases? What happens if surface area increases to the evaporation process? Rate of evaporation will be how the rate of evaporation will be. Suppose rate of evaporation and surface area. If surface area increases, rate of evaporation also increases. Now let's prove this one. So let's take plate. This is a plate, and this is also a plate, plain plate. Okay, the plates we will eat food. Okay, let's pour some 100 ml of water into it in this small plate, the same amount of water in very large plate, and put them in the in our under the sun. Okay, under the sun, put these two plates. The same amount of liquid is present in this plate and in this plate. In this plate it will take more time for evaporation, and in this plate it will take less time. Definitely this will occur, and this is because we can prove that the rate of evaporation increases when surface area increases. When surface area increases, rate of evaporation increases, and this evaporation is happening below boiling point, below 100 degrees Celsius. Anything happens below boiling point is nothing but evaporation. If it is happening at boiling point, we will call it as vaporization. Okay, so second one is also proved, surface area. Now we will talk about wind speed. What happens to rate of evaporation when wind of evaporation is when wind speed increases or when wind speed decreases. So, okay, this is proved. So now wind speed, when speed increases, when wind speed increases, rate of evaporation will also increase, because on windy day our clothes that we will know in our houses, we will use clothes like this for wet clothes to dry. Okay, if the day is windy, the clothes will become drier very soon. So this is our observation, right? So windy day, when wind speed increases, rate of evaporation increases. But theoretically, how we can prove when wind speed increases, rate of evaporation increases means, suppose in this case on windy day, the wind, what happens is that suppose this is rainy season, and the wind is coming. So on windy day, the surrounding particles, air is a matter. First of all, air is a matter because it is occupying space and it has some mass. So air is a matter, air particles are present, and air particles have more gap between the particles. So when wind occurs, these particles will move away from this region. Okay, so when air particles move away from this region, new particles will come, and these new particles can absorb water vapor. So suppose this is the environment, and there are some particles here, and here the liquid is present, and these are the air particles. These air particles will absorb this up to some extent only. Suppose they can absorb water up to some 100% only, not 120%, because when it reaches 100%, we will call it as saturation point. It will reach saturation point. So simply we can say saturation point by an example also. Suppose in a glass of water, in a beaker, if you add salt, some 10 spoons, it may dissolve. But if you want to add 11th spoon of salt, it may not dissolve, because the water saturated, the water will no longer can absorb the more amount of salt. But of course, if you heat this water, then they may occupy some more, then they may dissolve, the salt may dissolve. But we can say before heating this vessel, the liquid in the water reaches saturated. That means satisfied. Saturation point is nothing but satisfaction point. In the similar way, when on windy day, when wind flows, these air particles will move, saturated air particles will move, and new particles will come, so they can absorb more amount of water vapor. So that's why the clothes will become dry faster. Dryness increases, or you can say fastness of dry increases on windy day. So when wind speed increases, rate of evaporation increases. So we proved this one also. So in first three cases, when temperature increases or surface area increases or wind speed increases, rate of evaporation increased. But in humidity, it is different. It is different in humidity case, because humidity means nothing but humidity means water vapor in the air, amount of water vapor present in air. Water vapor present in air is nothing but humidity. So if in the air, you know that air is a matter, air occupies space and volume, and there are some air particles will have more gap between them, and these air particles will absorb water vapor from here, water in the form of water vapor. And if this water if they reach saturation point, that means satisfaction point or saturation point, they no longer can absorb more amount of water vapor. So if humidity increases, that means amount of water vapor present in the air will be increased. If this increases, so suppose initially the humidity may be at 60%, now 90%, then what happens to rate of evaporation? Rate of evaporation, here the liquid rate of evaporation will decrease, right? Because at 60% when a humidity is there, rate of evaporation may be some 20, so rate of evaporation some 50 or something like that. And if humidity, that means water vapor content increases so to 90%, then rate of evaporation may be 25 only. So just I am to imagine, I took these examples 50 and 25. So you can theoretically say that when humidity increases, rate of evaporation decreases. When humidity decreases, rate of evaporation increases. Okay. Here you can see that in case of on windy day, the clothes will dry very soon. The clothes will dry very soon. Okay, this is the best example. Okay, we can go to the next slide. The next question is, how does evaporation cause cooling? Evaporation causes cooling effect. The best example is that in summer we will use cotton cloths, and these two, and this is also a question, why we will wear cotton clothes in summer, and this and evaporation cause cooling, these two questions are related. Because if you wear cotton cloths, the sweat will be absorbed by cotton cloths very soon, and the cotton cloths, the sweat which is in the form of liquid will be evaporated very quickly. That means evaporation, rate of evaporation, you can say evaporation causes cooling, because the evaporation requires energy. We talked earlier that evaporation also requires energy, and this energy is taken from the surroundings. Here also evaporation occurs. For evaporation, the liquid to gas, here the particles will be very near to each other, and here there is gap. To break these forces of attraction, energy is required, and that energy in case of sweat is taken from our body also. That means our body has temperature at 37 degrees Celsius temperature, our body is working. So our body temperature will be taken, and at the same time surroundings temperature will also be taken by the by this sweat particles which is in the form of liquid. So our body will feel some coolness because of evaporation. So this example and this question both have the same answer, directly or indirectly, because evaporation causes cooling. Here also, if you see, if you take a thermometer, and if you see the temperature here, the temperature may decrease very less, but there will be decrease in temperature because evaporation causes cooling. It takes the heat from surroundings only. Particles of liquid absorb energy from surroundings to regain the energy lost during evaporation, makes the surroundings cool. Okay, the energy lost in this process, energy is lost. So to regain that energy, it is taken from the surroundings. So that's why surroundings will become cooler during evaporation. So evaporation is here is a evaporation causes cooling. And another example is best natural example is what we can do is, if you take nail polish remover, which is acetone. Nail polish remover is nothing but acetone, and acetone is in the powder form. Here we can say this is the acetone, and just take some amount of acetone into your palm, and the temperature of our hand, our palm, is sufficient for acetone to convert it directly to liquid, to vapor form, acetone, and this causes some coolness in our palm. So if you take in our hand some amount of acetone powder, this will convert from this state into vapor form, and we will observe some coolness in our palm. So this shows that evaporation causes coolness, because it is occurring below its boiling point. Okay, below its boiling point. Okay, if you know, you can move to the next slide. Temperature scales. We will talk about temperature scales here. Like in exams, centigrade temperature will be given, and they will ask to convert into Kelvin scale, or you can say Kelvin, in terms of Kelvin scale will be given, and they will ask to convert into centigrade Celsius. In the same way, Fahrenheit. In the same way, in terms of Fahrenheit. So that the formula is in Fahrenheit 9/5C plus 32. 9/5C plus 32. That means it's not 2C but nearly 2C. 9/5. If it is 10/2, it will become 2C. But is just for remembering purpose, I am telling this one. 9/5 of C. 9/5C plus 32. And T is equal to C plus 273. This sorry. This capital T stands for temperature in Kelvin. Temperature in Kelvin. And C stands for temperature in degrees Celsius. Okay. T equal to C plus 273. If at 0 degrees Celsius, temperature will be 273 Kelvin, because C equal to 0. At 100 degrees Celsius, 373 Kelvin. 100 plus 273. In the same way, if centigrade is given and asked to, if Kelvin is given and asked to centigrade, like 373 Kelvin is how many degrees Celsius? We know that T equal to C plus 273. 373 equal to C plus 273. C equal to 373 minus 273, 100 degrees Celsius. Like that you can calculate. In the same way, Fahrenheit also. Suppose 9/5 into C means 100 degrees Celsius, boiling point of water. In terms of Fahrenheit, 20 times 180 plus 32, 212. So 212 Fahrenheit. Like this we can convert from Fahrenheit to we can convert Celsius to Fahrenheit. In the same way, if you want to convert the Celsius scale into Fahrenheit, just write that 9/5C equal to F minus 32, and C centigrade equal to 5/9 of F minus 32. If you change this one, okay, just put this numerals and you can easily get this one. Okay, and the next thing is about two different states of matter, which are other than solid, liquid and gas. We talked earlier that there are another two states of matter like plasma and BEC. Bose-Einstein condensate. Okay, we talked earlier about these two states of matter, right? What is meant by plasma? Plasma means it is a state which is present in a sun. Sun is a star. In stars we will observe this fourth state of matter, in which there will be super energetic particles. There will be, the energy is very very high, and the gas is in the form of ionized state. Ions means like H plus, Cl minus. Here it is chloride ion, this is a hydrogen ion. So like this, in ion form, ionized the gas will be present. In a sun, the gas is helium gas in the form of ionized state. He is in the form of He4 plus, like that, He2 plus, that like that, in the form of ionization occurs. In fluorescent tubes also there is helium gas. We can say it is in the plasma state. In stars, like in sun, plasma created because of very high temperature. The temperature in sun is nearly 10 million degrees Celsius, and sun has a huge gravitational pressure. Gravitation, not gravitational force, gravitational pressure also. Force is nothing but when pressure equal to force by area, it is called as pressure. Huge gravitational pressure is present, and 10 million degrees Celsius temperature is present in stars. And because of this, what happens is deuterium 1H1 and 1H2, like deuterium, tritium, which are isotopes of hydrogen, converts into helium 2He4, and this helium will be present in the ionized form. So this state of matter is nothing but a plasma state. And another state of matter is Bose-Einstein condensate, BEC. What is meant by BEC? Bose-Einstein condensate means this BEC is formed by cooling of a gas of extremely low density. Suppose the density is 1 by 100,000th the density of normal air. Suppose this is the density of air, then we have to divide the density of air by 1 lakh times, 1 into 10 to the power of 5. 100,000th, that means like this, 3 5, so 1 lakh, 100,000, the density of normal air, we will get this extremely low density. So when you cool the air to this much density and to super low temperatures, we will form this state of matter, Bose-Einstein condensate. And Bose is nothing but Sachendranath Bose. He is our Indian, and he is a scientist, and he is the first one that he calculated, he given some calculations on fifth state of matter. He derived some calculations, and these calculations were used by the famous scientist Einstein, and Einstein further derived some more calculations and told that there will be a fifth state of matter, which is Bose-Einstein condensate. So that's why this is named as BEC. Okay, and the next question is these are the last questions that are given in the end of chapter in matter and our surroundings, like why ice floats on water, and why cotton clothes we have to wear in summer. I already told the answer for this one. Why cotton clothes are wear in summer? Because it will absorb sweat, and this sweat will be evaporated more quickly, and it will give some coolness effect in summer. That's why we will prefer cotton clothes, because it will absorb sweat more quickly when compared to silk clothes or some other clothes. Okay, that's why prefer cotton clothes, that too white color. Okay, and water droplets on, why water droplets present on cold water bottle? Suppose this is a fridge, and if you take water bottle from fridge and put it on a table for some time, this is the water bottle, and if you put it on a table, after some time you will the water is very cold, and we will observe some water particles on the surface of this water bottle, because this water vapor is not coming from the inside. This is not the water vapor from the inside, because there are no holes on the water bottle. If there are holes, we will not keep a water bottle in our bag, right? So there are no no water gaps, but we are observing water on the surface of this water bottle. How this is possible? Because the surrounding air has particles, and these particles carry some water vapor. We already knew that water vapor is absorbed by particles of air. These particles of air, when touches this water bottle, surface of this water bottle, the gas will become cooler. When gas becomes cooler, it will change its state from gaseous state to liquid state. So this gas will become liquid. That's how that is why we observe this kind of water vapor on surface of cold water bottles. And from this we can say that not only temperature can change the state of matter, but also pressure also can change the state of matter. Suppose in CNG and in liquefied petroleum gas, we are using the pressure to change the state of matter. In oxygen cylinders in hospitals also, we will use the same condition, like we will use the pressure. Under pressure, the oxygen gas is filled in a oxygen cylinder, and because of huge pressure, what happens is that this oxygen gas is stored in the form of liquid O2. Okay, so we can change the state of matter with the help of pressure also. Okay, we can move to the next slide. Thank you. This is the end of the chapter. Thank you guys.